more on energy. So now that we've had a discussion about the concepts of energy, we can move into some of the equations and the numbers. So we had three types of energy that we were going to be working with. The first is kinetic energy. The second was potential energy due to gravity. And the third is potential energy stored in the spring. All right, so kinetic energy, the energy of movement. What factors do you think go into the energy of movement? Like what would make something have more kinetic energy? So stop and think about it. Can you come up with a couple factors? So what would change things? What could I say? I could do this, it would have more energy, or I could do this, it would have more energy. What do you think? If you guessed that one of them was speed, you are right, definitely. And there's one more factor, and that is mass. So a more massive object moving at 60 miles an hour is going to have more energy than my little smart car moving at 60 miles an hour. So the equation for kinetic energy is 1/2 times the mass times the velocity squared. And now this is technically the speed because you can't square a vector. So this is, we're going to call it velocity squared, but it's really the speed squared because this is, you can't square a vector. Which means that this is not a vector. Woohoo! No components, no angles to worry about. So this is not a vector, it is a scalar. And the unit, mass is in kilograms, velocity is in meters per second squared, and if you match that all up, what you will get is what we call the joule. So that is a joule. Now the potential energy due to gravity. Again, stop and think about what would cause something to have more energy stored against gravity. So what could I do to a marker, or what could I compare? That's a better way to think about it. What could I compare to this marker to give something more stored energy? So think about that. What factors do you think we have to take into account? You probably guessed height as one. Absolutely. And height is definitely a factor. If it's something higher off the ground, it has more energy. And another factor is, maybe you got this one, mass. There's one more, which you probably didn't guess because it's so inherent in our thinking that it's like we're blind to it almost. And that is, well, what's causing this thing to fall? Why do we call it G here? Gravity. So mass times acceleration due to gravity times the height. Now keep in mind, this is 9.8. It is not negative 9.8, all right? Just the number. Anytime we see a G, it's just the 9.8. We take into account direction another way. All right, MGH. So the units here would be a kilogram. Gravity, meters per second squared times height, which is meters. Okay, so kilogram and kilogram. 2 meters up top, 2 meters on bottom. That is equal to a joule. All right, third one. Potential energy stored in a spring. So again, what could you do to get more energy stored into a spring? The other way to think about it is, what would make it harder to store the energy in the spring? I'm not sure if that's phrased right, but think about that. What could you do to change that would cause something to have more stored energy in a spring? You probably said, I'll just do it this way. Stretch it out more. Yes. So the extension or compression, or delta X for a spring, definitely is a factor. The other thing is the spring constant. So if you stretch a slinky 10 centimeters versus a car's leaf spring 10 centimeters, yeah, there's a different amount of energy in those two. The unit here is kind of sneaky because we have a Newton meter times meters squared. Yeah. So that's a Newton times a meter. Well, that was the definition of a joule. So, okay, we're good. These are all joules. So here's our definition of these three types of energy, and these are the three that we're going to mostly be using. One of the key things that you have to decide when you're doing problems involving energy has to do with the potential energy due to gravity. In order to use this we have to pick an origin. We have to say the height from where. So you have to pick an origin every time you do an energy problem if you want to use this equation, because height compared to what? And your brain is probably saying, well, duh, it's the floor, it's the ground. Maybe, maybe not. You actually can choose. And if you choose one origin and the person working with you chooses another, it's fine. The math will work out. You'll still get the same answer. But like the pivot point with torques, if you choose a smart origin, if you're smart about how you choose your origin, how about that? Your math can be a lot easier. Give you an example. I am going to take a marker, okay, marker's on the floor. I'm going to lift the marker from the floor to here. Okay, so if I did that, then the origin that would probably make the most sense is the floor. However, if I were to take the marker from here and lift it up to here, then what would the origin be? I could pick my origin to be at the base, right here where it started. I could pick it at the floor as well. It would just have some initial height to start with. They're going to get you the same answer. But just think about, what is your origin? My preferred origin tends to be the lowest point in the whole problem. So the lowest point of any object in the problem. That tends to be what I want. But again, doesn't matter what you pick. Math will make it work out. All right, next up I want to do an example. Let's do an example with some numbers even. Woohoo! All right, and the equation sheet has those 3 definitions on it. So don't worry about me erasing it. And hopefully you also have it in your notebook by now. Okay, so let's do an energy problem. I'm going to toss a ball straight up, and it goes 1.2 meters before it comes to rest at its maximum height. So toss something straight up, 1.2 meters. That wasn't actually too bad. That's probably about 1.2 meters. So picture, as always. So we start with something here, and it's moving up, and then it ends up here, and we know that this distance is 1.2 meters. All right. I like, when I'm doing energy problems, to always signal to myself if there's velocity or not. So I tend to write velocity equals 0, or put a little arrow showing the direction of the velocity. And it's just something I do to help me figure out what the problem's like. Okay, so what we want to know is, what is that initial velocity? So I'm going to label that initial. Now, if you go way back, weeks and weeks, we did problems like this back in kinematics. So you would be able to solve this with kinematics. Now we're going to take it with an energy approach, and you'll see that it's faster. It is faster. So why didn't you give us this before? Because that's the way physics textbooks tend to be written. And yes, I don't know why. So what is the initial velocity? Okay, the equation that we have been using is the initial energy plus or minus any changes in energy equals the final energy. All right, and I'm not going to use this right here. There's nothing doing work. I'm going to ignore that change. And we'll talk more about work in a little bit. So, initial energy. What types of initial energy do I have? 3 questions to ask yourself. Is something moving at the start? Oops, I should label it. Initial, final. Is something moving at the start? Yep. I have initial kinetic energy. Is something above its lowest point? No, it's at its lowest point. Is there a spring? No. So initial energy, just kinetic. Final energy. Then we've got, let's see, is something moving? No, we have no velocity, no kinetic energy. Is something above its lowest point? Definitely. We have potential energy due to gravity. No spring. So, there you go. Okay, great. 1/2 mass, initial velocity squared, equals PEG mgh, and that's the final height. We don't know the mass of this thing. It could be a marker, it could be a ball, it could be a smart car. We don't know what it is. And it turns out it doesn't matter, because mass here, shoot, shoot. And back when we were doing kinematics, mass didn't matter. So that's good. We're getting the kind of the same conceptual thing. Mass doesn't matter. we want to know this. V initial squared equals G times H final. To get rid of the 1/2, put a 2 on the other side. V initial equals the square root of 2 times gravity. Remember, just the number, not negative. 9.8. H final. What's the final height? And, I didn't choose an origin. Bad me. So here I say, this makes sense right here. I'm going to choose this as my origin. That means the final height is 1.2 meters above my origin. If you do that math, you would get what? What do you get? 4.85 meters per second. Okay, now what I'd like you to do is bring your mind back to kinematics and solve this with kinematics. So hit pause, solve it with kinematics, see if you get that same answer. See if you do. All right, hopefully you did. Hopefully you did. It actually should have turned out to be the exact same calculation. It's just we would have said 2 times A times X. So, yes, it should be. Now I'm going to solve it with a different origin. So what happens if I put my origin here? Okay. I need to actually redo this to see if that's going to be the same. I don't know if that's going to be the same or not. Initial energy, well, my initial's still here and my final's still here. So initial energy, yeah, I still have kinetic. It's still at its lowest point. There's still no spring. Initial's still kinetic. Final energy, yeah, okay, it really is the same. Which means my equation is going to be the same. All right, 1/2 mass, initial velocity squared, equals mass times acceleration due to gravity times the height. Masses will cancel. And then, okay, look at this. V initial squared equals 2gh. V initial equals the square root of, this is being interesting, isn't it? 2 times gravity, 9.8, times the height, which is 0. What did we do wrong? What did we do wrong? Okay, so in this case, what we have to think about is the fact that with the origin here, we start off not at what we call ground level, not at our origin. Anything that is not at the origin needs to take into account potential energy due to gravity. That's sneaky, isn't it? So really this is a different equation. This does not work. Well, that means we have to erase. So what we're going to do is go back to this step and say, okay, so what do we have to do to change this step to make this true? What I just said is that if you're not at the origin, you have to take into account height. All right, that means when we are here in our initial point, our initial condition, we have some stored energy due to gravity because we are not at the origin. So there's some stored energy due to gravity. And here, if the origin is there, my height is 0. So here, my height is 0, which means there's no energy to end with, excuse me. Now you might say that's close to what we had, but there's a weird negative sign going on. Because we've got that initial is equal to negative, PEG, 1/2 mv initial squared equals negative mg h final. Only it wasn't h final. It was h initial. Okay, so this is initial, which means this is my initial height. Mass cancels, and we can still do v initial squared equals negative 2gh initial. V initial equals the square root of negative, and here I go, oh no, square root of negative, not physically possible. But no, we're okay, it's okay. Because what was our initial height? Our initial height was 1.2 meters below the origin. Below the origin, which means that my equation will be negative 2, 9.8, negative 1.2. And you will get the exact same 4.85 meters per second for your initial speed. But you can see that having the origin in a more sensible place makes life a lot easier, and you don't have to worry about these negative heights, because negative heights, I don't like that. So I tend to choose my origin at the lowest possible point of the problem. But the math comes out exactly the same if you choose a different origin. So if you pick a wrong origin and the math is getting really ugly and like, I can't figure it out, try picking a different origin. See if that might help you solve the problem. But remember, if you pick a different origin, your equation might be different. Okay, and I think that's all I'm going to do on energy right now. Next up, we will talk about work and what work is and how we find it, how we define it, all that good stuff. But for now, we have energy, kinetic energy, potential energy due to gravity, potential energy due to a spring, and voila, we can do all the math and solve these problems. Good job.